Hi, welcome to the lecture Feature Extraction in Time Domain. So why features? Why should we extract features from the speech signal instead of directly dealing with the speech samples? There are two main reasons here. One is speech data is redundant in nature. If you take 16 kilohertz sample speech, then you would get 16,000 samples per second. That is too much of a data to transmit over a digital line. So there's a need to compress the speech signal for efficient and cheaper transmission. Another main reason here is there are multiple sources that are embedded in the speech signal. Speech contains information about the message that has to be transferred. It contains the information about the speaker. It contains the information about the emotion and the stress in which the speaker has spoken that sentence. If you are building a speech recognition, then you would require only speech or message specific part of it. If you are building a speaker recognition, then you would require speaker specific part of it. So there is a need to extract meaningful and only the required representations from the speech if you are building a specific application. So what is feature extraction? In simple way, you can define feature extraction as a process of deriving a compact and useful representation from the speech signal. There are many features which we are going to talk in this lecture, but for the time being, let's consider energy as an example feature. So how do we define energy here? We define energy as equation which is shown here, where it takes the sample xk, squares it up, and then sums it over the analysis window and divides it by the length of the analysis window. So n here is the length of the analysis window and x of k is the kth sample. So now let's say this is an example speech signal which we have taken here, and for the time being let us assume that we have put the analysis window over the entire speech here and then plug that equation, energy equation, which we saw in the last slide. So that means if n is equal to 30, then the energy obtained here is a single value, and then that is what we have plotted here. So it's a single value or single point which represents this entire speech signal. It is clear that this is not a good representative because it doesn't talk about, or it doesn't tell you what is there in the speech signal, or it doesn't describe the speech signal in any meaningful manner you can imagine. So this is not a meaningful representative. So if we put our analysis window over the entire speech, then we are not going to get a meaningful representative here. So let's say we go with an analysis window where it is put over each sample. That means if n is equal to 1, and then we plug in the energy equation, and then this is the energy sequence or energy samples we get here. So what you can observe here is that we are getting an energy value for each sample corresponding to the speech signal here. So this information is too detailed or as good as the speech itself. So what do we want here? So here I am showing a meaningful and compact representation. So you can see that this is a smooth energy curve which is kind of intuitively which can tell you that it's a good representation for the speech signal here. So that means whenever there is a high energy, you can see a peak in the energy, and then whenever there is a low energy signal here, and you can see a dip here. That's how it goes. So it's a smooth signal which depicts the which describes the speech signal in a much better way. So how to obtain this energy curve here? So one way to obtain, or the way to obtain this energy curve, is to shorten your analysis window, not too long, not too short. That means we don't want to have the analysis window or the entire speech, or we don't want the analysis window to be put on each sample, but we want the analysis window to put on a certain shorter region, which you can see here. So there is a speech signal here, and then we divide the speech signal into shorter regions. So our analysis now will focus on each of these shorter regions. So typically this analysis window size is 320 samples, that is 20 milliseconds. So you should remember that this is important. So we process the speech signal by using an analysis window of the order of 20 milliseconds. That means we take the speech signal, break them into shorter regions, and analyze them, or observe the features, or try to derive the features from that shorter region. So how to use this short analysis window? So now this is a short analysis window here, and then what I'm showing here is a zoomed version of this signal. So we take this short signal and then give it to plug into our energy equation, and then get energy value here. So then now we move our analysis to the next window, which is here, and we do the same process. That means we take that part of the signal and then plug in the energy equation and get another value here. So similarly I do the same process for all of the analysis window here, and then correspondingly get the energy values. So finally I come to the last window and I repeat the same process, and I get the energy values here. So if I plot these energy values, so that's what I'm going to get here. So for each analysis window I get a point here. So and then I connect all of these points, the red stars, through a line, and that's what the smooth curve is about. So this is called energy curve or energy contour. So this is the basis for our feature extraction. So you should understand that speech is processed in terms of short regions, and then we extract from each short region a point or a vector. In this case it's a single point which represents the energy of this signal. So let's look at more carefully why we are so excited about this representation. So if you see in the speech signal, this is a voice signal, this is another voiced segment, this is another voice segment, and then there are two unvoiced segments here, one here and one here. So what we are observing here is that whenever there is a voiced segment, the energy is high, which is here, and whenever there is an unvoiced segment, the energy is low. Similarly, now there is a voiced here, there is a high energy, and then there is unvoiced here, there is a low energy, there is a voiced here, there is a high energy. So you can see the usefulness of this energy as a feature. If the energy is in the analysis window is high, then it implies that the frame we are talking is voiced. That means it can be a vowel, diphthong, semi-vowel, or voiced consonant. If the energy is low in the analysis window, then that frame, or like the analysis window is also referred to as frame here, then the frame is unvoiced. That means it can be an unvoiced consonant or a silence. So how we can use this energy as a feature, or more or put into an application? We can use this energy as to detect voiced and unvoiced regions, and we can also use this energy for silence and non-silence detection. So what are the other features which we are talking about here? So we are going to talk about energy, which we did, and then zero crossings, and then pitch or fundamental frequency. So what is a zero crossing? It's kind of very clear. A zero crossing is said to occur between two samples, x of t and x of t plus 1, if the signs of these two samples do not match. That means if one is positive value and another one is negative value, then there's said to be a zero crossing between these two samples. I'm just showing an example here. So this is a zero crossing point. So you can see this is another zero crossing point. This is one, this is another, this is one, this is one, this is one, this is one, and this is one zero crossing point. So whenever the signal crosses over this zero line, that's what we call it as zero crossing.